In this video, we take a look at the last section that involves convergence and divergence tests for series. We have the ratio and root test. In this video, we'll just handle the ratio test. So I want to go through that here, just pretty much go right into it and write down the stipulations of the test and how we know when a series converges, diverges with this ratio test. Okay, so what we look to do here, the ratio test says that if we have a series where the nth term is always non-zero, right? So we can't have any zero terms, then we have three kind of outcomes from this ratio test. The first is that the series converges absolutely when the limit as n goes to infinity of absolute value of a sub n plus 1 divided by a sub n is less than 1. Okay? So this is a test for absolute convergence. That's kind of embedded in the test. We don't have to do another test. Those absolute values are already there. So anytime we do the ratio test, we have to pay attention to those absolute values. But that means that this can be used on alternating series as well, right? Because of those absolute values. So anytime that limit there is less than 1, we have a convergent series. So here is a nice situation where I have a specific limit that I'm taking and I'm looking for a value that is less than 1. The second option, or the second potential outcome, is of course divergence. The series diverges when that limit there, same limit, is larger than 1. Okay? So if I take this limit and I get 4, that's bigger than 1, my series diverges. I'll go through some examples shortly. There is one third potential outcome, and that is just that the test might be inconclusive. The ratio test is inconclusive when that limit of an plus 1 over an is exactly 1. So basically this test doesn't have enough, it's not strong enough in a situation like that to explain what's going on. But if the limit is larger than or smaller than 1, then we have an outcome and we know what's going on. I want to do a couple examples here and just see kind of what situations we end up in and when the ratio test might be useful and when it maybe might not. As you've seen from some of the other sections and assignments, that you don't necessarily have to do a specific test. A lot of the times the test kind of lends itself to a specific series or vice versa, when you're dealing with a specific example. So it's not necessarily always do this test, but this ratio test will be something that we continue with in the next couple sections. So this example here, determine the convergence, or divergence of the series from 0 to infinity of 2 to the n divided by n factorial. Okay, so I want to say a little bit about factorials here. We remember those from the beginning of the chapter. It's a nice condensed way to write a product of all the terms leading up to n, right? So when n is 0, that's the product of all the terms leading up to 0. That's just 1. That's defined to be 1, 0 factorial. A lot of the other tests we do, integral test, I don't know how to integrate a factorial. So that is pretty much out here. This doesn't really resemble p-series, a little bit of geometric with the n in the numerator, 2 to the n, but there's not going to be a common ratio from each term to the next because of that n factorial in the bottom. Okay? In fact, factorials are a nice indicator. Factorials are an indicator that we want to use, the ratio test. And the ratio test works rather nicely with factorials. And I'll show you why. What I want to come up with is a sub n and a sub n plus 1. A sub n is, of course, just the nth term. That's 2 to the n over n factorial. And a sub n plus 1 is the next term in the sequence of terms, right? So that next term is going to be 2 to the n plus 1 over n plus 1 factorial. You basically just replace any n with n plus 1. Now I know I'm going to need a limit where I have a sub n plus 1 divided by an. So to do that, first what I want to try to do is mess around a little bit with these expressions and see if I can, I'm probably going to get some cancellations when I divide those two because they're very similar expressions. So what I'm going to do is take a sub n plus 1 here and take it apart a little bit. In the numerator, I see 2 to the n plus 1. That's the same thing as 2 times 2 to the n. And also in the denominator, I know n plus 1 factorial. I can pull off as many terms as I want, but it's probably beneficial to pull off the first one there, that n plus 1 as a factor, and leave the n factorial left over. Okay? And again, you'll see why I do this here when I create my limit. I write my limit, and I'm dividing an plus 1 by a sub n. And I'm just going to write those in here. And we start to kind of see how things might cancel. Now, I'll do this kind of all the time, but notice I'm dividing by a sub n. To simplify this, I'm going to multiply by the reciprocal of that guy. So you'll see this a lot of the time where you have a sub n plus 1 times the reciprocal of a sub n. So this is, excuse me, this is what do I have here? A sub n plus 1 times 1 over a sub n. We're going to do that just about all the time. And then we see these cancellations, right? In the numerator, there's an n factorial. In the denominator, there's an n factorial. Those disappear. In the numerator, there's a 2 to the n. And in the denominator, there's a 2 to the n. So what I have left, it looks like that's all that cancels. What I have left is then the limit, absolute value of 2 over n plus 1. Okay. The ratio test will just about always play like this. You're going to plug in n plus 1 for n. You're going to divide the next term by the kind of previous term or the nth term, and then you're going to have some cancellations. And after that, we have to take a limit. Now, what I notice about this here, I got these absolute values. We tend to ignore those. We can't ignore those, and I'll do some examples a little later where this shows up. However, what happens here is I have 2 divided by n plus 1. And I know my n's are all going to be positive numbers. So this expression that I have is really all positive. So these absolute values I can kind of ignore and really just take the limit as n gets really big. I'm dividing by larger numbers. This limit is 0, which is less than 1. So I can say by the ratio test, the series 2 to the n over n factorial converges, and because the ratio test is the way it is, I can say it converges absolutely. Okay, so let's play again here with a slightly different series and see what happens. This one looks a bit more geometric, maybe. I see a 2 to the n plus 1, 3 to the n, so I'm seeing maybe components of a geometric series, but that n squared in the numerator really makes it not geometric. Another situation where the ratio test might be nice, and that's just because it's geometric-like, it's close. You might try a comparison here. It just depends. So what we've got, if I write my limit down, but so this is just a little bit about what I said before. When I write my limit down, I'm always going to have that a sub n plus 1 divided by a sub n, and I'm always going to treat that like a sub n plus 1 times the reciprocal. So I'm going to go to that right away here. I plug in n plus 1 for n. So for every n, in my series there, I'm replacing it with an n plus 1. Okay, so that's why I see n plus 1 squared. It's going to be 2 to the power n plus 2, and then 3 to the n plus 1. And I'm going to multiply that by the reciprocal of the original nth term. So that's going to be 3 to the n over n squared times 2 to the n plus 1. So again, those guys are the same. They're the reciprocal of a to the n, and what I've got underlined there in blue. Okay, we start to manipulate, right? These are going to be very similar expressions. We're going to have some cancellations, but I'm working with a lot of exponents here, so I have to be a little careful. I'm going to start breaking things apart. I can't really change much with the n plus 1 squared, but I can break off a 2 from 2 to the n plus 1, right? That's the same as 2 to the n plus 2. This guy here is all the same as 2, I can't write there, 2 to the n plus 2. Right, so I've pulled off 1 because I see a 2 to the n plus 1 in the denominator to cancel with. Same idea with 3 to the n plus 1 in the denominator. I can write that as 3 times 3 to the n. I don't really have to make any changes with that guy in yellow, but now I start to see my cancellations, right? These 2 to the n plus 1s disappear, 3 to the n's disappear, and that's really it. I'm just going to try to collect what's left. In the numerator, I have 2 times n plus 1 squared. Sorry, I almost said factorial. And in the denominator, I have 3 times n squared. Cool. Cool, cool. So a couple things here. That's going to be a completely positive expression because numerator has a squared piece, denominator has a squared piece, and the 2 and the 3 don't make anything negative at any point. So I can drop absolute values, and also this 2/3 I'm going to bring out front of my limit here. And then I have n squared plus 2n plus 1 as a result in the numerator. To evaluate n plus 1 squared in a limit, I could use some L'Hopital's rule, but I think it's a little bit easier to just expand to FOIL and then evaluate the result. Dividing everything through by n squared, I come up with limit as n goes to infinity of 1 plus 2 over n plus 1 over n squared. And as n goes to infinity, the only thing I have left there is a 1. So this whole limit here, the ratio test, gives me a 2/3 times a 1. And 2/3 is definitely less than 1. So this series converges absolutely by the ratio test. The series, this guy here, n squared 2 to the n plus 1 over 3 to the n converges, and we say it converges absolutely. So it's actually a relatively quick test to apply. I want to do one more example here and just show you some of the other intricacies of this test. But for the most part, it's a relatively easy thing. It's widely used. We'll use it a bit in the next, like I said, in the next couple sections here. But I think you've got the gist. Let's just look at one more example. And I didn't do any alternating series here, but what happens if you've got like a -1 to the n? That's pretty much just going to disappear when you take absolute value. So there's not a lot to worry about if you're doing ratio test on an alternating series. But just be aware that it's a thing and it can happen. What I have here is n to the n over n factorial. This is an interesting one. And it's more interesting because of the calculus going on behind the limit than it is for the actual series. But what happens here is I have the limit as n goes to infinity. For every n, I plug in n plus 1. So I get that guy there. N plus 1 to the n plus 1. It's a little weird to work with, but there it is. Divided by n plus 1 factorial. And times the reciprocal, where I have n factorial over n to the n. So I'm going to break some things apart again here. I see that n plus 1 to the n plus 1, this guy, I'm going to bring off a factor of n plus 1. So I have n plus 1 I'm also going to split apart my factorial. I have n plus 1 times n factorial, and then n plus 1 times n plus 1 to the power n. Okay, and that's because I'm trying to keep the powers kind of the same so I can manipulate them nicely that way. I see a power n, I see a power n. I like that. That's what I want. I notice that the n plus 1s and the n factorials are going to disappear. And that leaves me with the limit as n factorial, as n goes to infinity, of n plus 1 to the n divided by n to the n. And I'm taking a limit here. That's kind of a gross thing, but again, these powers are the same. So I'm going to bring that out. I'm going to bring that power of n out and leave it with just n plus 1 divided by n, all to the nth, right? Properties of exponents says that's the same. And when I divide that numerator by n, I get a 1 plus 1 over, 1 plus 1 over n. This is that special limit. And it happens that that limit is e. And let's show why this is an indeterminate form. It's an indeterminate because I've got 1 to the infinity. This is a situation where we use our natural log. And I'll go through that process here in purple. But using properties of logs, I take natural log of both sides of what's inside my limit there. And just what I use to substitute, say, some y. I manipulate this. I use properties of logs to bring down that n, the exponent, the outer exponent there. And what I want to do, I'm eventually going to apply L'Hopital's rule, but I need a quotient to do that. Multiplying by n is the same as dividing by 1 over n. So this limit, when I take the limit of that new expression there in purple, I have an indeterminate form again. The numerator is going to 0 and the denominator is going to 0. So I can apply L'Hopital's and I take derivatives. I get 1 over 1 plus 1 over n. And then the derivative of 1 over n is minus 1 over n squared. Denominator is just minus 1 over n squared. So actually those two expressions are going to disappear. These guys are going to cancel and I'm left with 1 over 1 plus 1 over n. And the result there is indeed 1. As n goes to infinity, 1 over 1 plus 0 is 1. Okay, but this is all the limit of the natural log of y. I want the limit of y, 1 plus 1 over n to the nth. So what I have to do is then kind of use my exponentiate property. I have to exponentiate. E to natural log of y is the same as the limit, is the same as y, is the same as 1 plus 1 over n to the n. So this limit is all e to the first, which is bigger than 1. E is bigger than 1, so the series diverges by the ratio test. Okay, I wanted to do an example where we got divergence. I didn't do an example where the series or where the test was inconclusive. You'll see some of those come up every now and again. You'll think the ratio test is the test that you want to use, and it just so happens that it doesn't really give you any information. So when that happens, you'll have to try to apply a different test. There might be some practice on the WebAssign assignment for that. Otherwise, I just want to see that you can apply the ratio test, work with this limit, do the manipulations, and understand when the ratio test gives convergence, divergence, and is inconclusive. Okay, thank you for watching.